Okay, well, good afternoon, everybody. Welcome to this presentation on real-time data and how we can use real-time data to provide insight and actionable information to improve reliability and efficiency. So just a little bit about me to start with. I am Alexander Dixon. I'm based in Aberdeen. I've got 16 years of experience with building real-time data solutions. And I'm currently leading a team of 14 real-time engineers who are working for an oil and gas major. Got quite a bit of interest in home automation using Home Assistant and all of the kind of tech and tools around there. And within ITI, I'm working in what we call our digital operations team. So Chris has mentioned that within the ITI organization, we have solutions that are based on control and safety systems that are engineered out of other offices, but Aberdeen is our hub for digital operations. When we're talking about digital operations, the digital operations team partner with our customers to transform data into information to solve problems. And we often partner with customers who want to solve problems that they don't know how to solve, or they don't know what problem they need to solve even. These companies, for me, I'm predominantly in oil and gas, so they include operators and super majors on that side, but we do also work with power and infrastructure and food and beverage and a bunch of other customers. And often our customers will come to us with problems that are potentially not well defined. We might hear something like, we spend a couple of hours a day collecting data manually, or I need to be able to analyze data from this equipment more efficiently, but I don't know how to do that. Or maybe even this piece of equipment we've got keeps breaking down and we need to get on top of that, but we're not sure how to achieve that. And our team will work with engineering staff and other staff in those organizations to take those woolly statements and use our innovation to transform those problems into solutions with clever solutions. That might be providing a system that collects data automatically instead of manually. It might be to use analytics to predict future failures or something like that. Many of our customers see the innovative things that ITI deliver as part of a long-term journey. So what I'm going to do today is focus a little bit on how analytics can help us to increase efficiency and reliability. Our key input for all of that, though, is data. And we use data from many sources, mainly physical measurements like pressures and temperatures, or status indicators, or level indicators, things like that, that would be coming from a control system that my colleagues would potentially be looking at installing. So an integrated control and safety system, something like that, that collects real-time data. And typically, in an offshore environment, an offshore oil environment, we might be looking at 50,000 physical measurements that we can be collecting in real time into a real-time information system that can then be used for analytics to better serve the plant and whatnot. Typically, the ICSS systems we would refer to as operational technology, which I'm hoping is a term that you're already familiar with. But we might also use data from other systems like standard databases and things like that. So let's just have a quick look at that. On the left-hand side of this diagram, you can see what we would traditionally talk about as being operational technology, physical plant, sensors, controllers. Previously, in the past, systems that would have been completely isolated and relatively unknown to Joe Public, who's out and about, who will have a good idea of what's going on in the IT space, but not a clue about operational technology. These systems are often bespoke and designed meticulously to complete a particular task in a predictable and measurable way. So to control the plant safely, whatever that is, whatever that looks like. Downtime is not acceptable. Redundancy, security are key. On the right-hand side, we see the information technology systems that we're all now used to. And indeed, we're sitting here today on a Teams call. A few years ago, that would have been something that would have been relatively early in its infancy, and now it's widely adopted in the IT space. Downtime's generally accepted. If something doesn't work in IT, then switch it off, switch it on again. If it doesn't work, it's okay to try again. And that kind of thing is not acceptable in the operational space. These worlds used to be separated, but they're now much more aligned. And I'm sure there's examples in your own personal space or your own personal world where you've seen that. And Hive from British Gas is a great example. I'm sure I'm not the only one that's got a house full of internet connected gadgets that can seemingly switch themselves on and off at their own whim. And I'm probably not the only one that's asked Alexa to turn the heating up or down in the last few days. If we have that sort of integration happening at home and that sort of data flow happening at home, then why can't we have that in industry? And that's where a lot of the solutions that we build come in. So coming back to the title of the presentation, how can we increase reliability and efficiency? Well, reliability and efficiency, we could be talking about a lot of different things here. We could be talking about physical equipment, which we're going to put a lot of focus into. It doesn't really matter if that's a multi-million-pound compressor on a gas chain, or whether that is an oven in a bread-making facility. The business requires that piece of equipment to be reliable and efficient in its task. But alongside the physical equipment, we've also got other assets, if you like, that we need to be able to use their time effectively for. So if we've got a rotating equipment specialist or a subject matter expert that has a limited time in their day, we really need to be able to help them focus on what their priority tasks should be. And that's something else that data can help us achieve. So two things I'm going to look at during our time together just now: use of analytics to transform data into information, but also providing the right person with the best information in an effective way, so that we can get the efficiency out of all of our collective knowledge that's in our engineering teams as well. So before we step into the clever solutions, I thought we'd take a moment just to have a think about how data is typically used today. And we find that in a lot of situations, data is still predominantly used after the fact, to go and look at something that's happened in the past, to investigate an issue, why did this occur type investigation. And typically, our control and safety systems that we're building are reactive. And that is absolutely what they're there for. They're there as a last line of defense to protect people, assets, environment, the company, finance, all sorts of things. And they do that job really well. They're not designed to be proactive and help us be effective and efficient in many cases. So how do we become more proactive with our data? Well, if we can take our data from these systems and use analytics to combine that with other sources of information, we can then use that to drive action. So what we're going to do in the next few minutes is we're going to have a look at some examples of how we can do that by taking real-time data, transforming it into information to help the operator or the engineering resources to get more efficiency and more effectiveness out of that piece of equipment. So display that I've got here shows a typical health monitoring screen that we would see in a real-time information system. Now, it's probably worth mentioning that the real-time information systems that we generally use, it's a product called Pi from OSIsoft. So these displays that we're looking at are actually built in the OSIsoft Pi system. This display shows a typical health monitoring screen where we're using analytics that are specifically designed to bring our attention to the issues with this high pressure compressor in this case. We're going to step through the techniques that are used to drive this type of display and to provide an overall health-based display to direct people in the right direction. So the first thing we're going to do is we're going to focus on this section in the middle of the display where we can see individual instruments or pieces of data that are being presented to us. And we're going to have a look at how we can detect something that's maybe going abnormal or out of its normal conditions. So if we break that down into a single signal, then I'm sure that you're all going to recognize what I'm going to describe here with a single full range signal. That might be a temperature, or maybe actually a level might be a better one to explain. And if we've got a level indication in a tank, it's going to have a full range signal of 0 to 100%. We're going to have defined in our instrument and control system a normal operating limit, which is going to be quite wide in the middle of that range. So that the normal operating limit of that tank might be 10% to 90%, for example. Then we're going to have a safe operating limit, which is the limit where we're approaching the operating range of the equipment. It might also be known as a high or a low alarm. And then our final line of defense is going to be our safety system, where our safe design limit is set. And if we breach that safe design limit, we're going into territory where it's no longer being used in the way that the system's been designed. It may no longer be safe, and it may almost certainly will follow into a situation where a trip or a shutdown will occur. So safe design limit, you might also know as a trip point, or the high or the low alarm. Again, the ICSS is doing a great job of doing what it was designed to do. But if we look at that in the normal operations, I'm showing you a trend here of a temperature. We can see that that temperature is sitting in a normal range of 118 perhaps to 140 degrees centigrade. If that temperature was going to start to increase slowly, then there's a potential that we've started to head towards a situation which is abnormal, and we might not realize we've got there until we hit that high alarm of 180.5. Clearly, there's quite a distance between the current value of 117 and the high alarm of 180.5. And if we can detect that abnormality quicker, then what we're going to do is we're going to give our engineering resources an opportunity to deal with that situation before we hit the high alarm, and certainly before we hit the high alarm where we end up with a process trip. So how can we go about trying to make that a little bit more reactive so that we know what's going on sooner? Well, what if we were to add a dynamic operating envelope which can detect when something is abnormal? So this could be calculated in several different ways. But if we put a band round about what we think is normal and use a mathematical function to be able to determine when something's starting to drift out of normal, then we can then use that to alert earlier. So let's have a look at a really simple example of that. This is the same signal we were looking at, and what I've done is I've used an average function to give me a high and a low band round about it, which is the pink shaded section. And by using that, we can see there's a couple of points at which we become quite close to abnormal if we're taking that as our normal. Now, obviously, determining what normal is a different conversation and needs a little bit of thought about how that piece of equipment operates and the nuances around the data. But for our simple example here, that's fine. If we had a situation where the value is to continue out of that abnormal range, then we could start alerting on it. The configuration of this might change based on the type of data, the type of equipment, the frequency the data is available. We might actually want to correlate it to another value in our real-time data set. It really just depends on what the actual piece of equipment that we're looking at is. So using that technique, we can potentially detect when something is heading for abnormal, and then we can use that to determine how far away from normal we are. So here's a trend of the same kind of information that's showing us the deviation from normal being 0 over time. Now, that's useful information, but it's quite difficult to make sense of that information with the context in your brain. So this is where providing the right information in the right format is really important. So if I display that in this format here, we can see if normal is in the middle of the triangles that are shown, we can see how far away from normal we are. Now, on a single signal like that, that's useful. However, when we start monitoring things system-wide, that becomes an awful lot more useful. So if I show you this next display, we can see that detecting deviation visually is much easier. So we can see here we've got almost 24 analytics running there. We've got different parameters being looked at, but we're immediately drawn to the high-speed gearbox, where we've got something going on with the non-driven end and the driven end, and also the lube oil system. And we immediately know from that that that's where we should be focusing our attention, because we've got something that is way far away from normal in those two subsystems. So the user experience is really important to being able to use the data that you're presenting. It's really key to make sure that we can do all the clever analytics we want in the world, but if they're not presented well to the end user so that they can be consumed easily, then you might not get the benefit out of them that you're actually expecting. So I want to go on and describe another type of analytic that we could use to provide early detection. So this one's called a paired signal. And typically in a critical situation, we would have two signals that are monitoring the same thing feeding into our systems. So if we had a temperature, a critical temperature in our environment somewhere, it's likely that we're feeding a temperature sensor into the control and safety, the ICSS, the control and automation system, being more precise about it, and a completely separate signal that's being fed into the safety system. Now, it's more than likely that our control room operator is going to be monitoring the control and automation system signal. They may never look at the safety system temperature signal that's coming into it, which is fine in normal operations. If everything is going well and everything's maintained well, that's great. However, if something goes wrong and we end up with a deviation between those two signals, we might end up in a situation where there's an unplanned outage or a trip because the safety system has detected an erroneous signal coming in that's caused it to believe that we're in an unsafe condition. If I let you see a couple of trends here, we can imagine that we've got the blue trend coming in from our temperature sensor hitting the control and automation system, and our orange ones hitting the safety system. They look pretty similar if you're eyeballing them together, But if I lay them on top of each other, you can see there is actually a deviation there. And that might be because our signal going to the safety system just needs to be calibrated. It might be indicative of a fault or a wiring fault or something going on there. But it's quite obvious when we lay them together that there's an issue. And it might even be the case, looking at this trend, that on the left-hand side, things are closer together than on the right-hand side. So it might be that they're actually deviating on over time, just slightly, but enough that when that deviation splits a little bit wider, we could end up with a potential trip. So again, we can use analytics to help us in this situation by monitoring both signals coming into our real-time information system. We can calculate what the deviation between the two signals is. So we can see in my trend there that in the past 2 hours there, we've had a bit of a step change. In fact, we've had 2 step changes where things have become less correlated. And again, using the deviation calculation, it's simple to be able to attract attention to issues as they occur and before they become a process interruption. So what we're doing with those 2 different types of analytics there is we're increasing our ability to respond. So if we think about a signal and our eventual process trip and downtime, then our last line of defense there is our safe design limit. If we've breached our safe design limit, the safety system is going to kick in and shut that system down. Typically, that's going to happen in milliseconds or seconds. We've got no time to react. By the time we've hit that safe design limit, that is it. Our ICSS normal operating limit might give us a little bit more time to respond. We might get some minutes, possibly hours, depending on which situation we find ourselves in. But we might get some time between an operator getting an alarm on their ICSS workstation and the process trip eventually happening. And it gives us a bit of time to respond. However, if we implement our dynamic operating envelopes and start detecting things that are abnormal, then we're extending that period where we have the potential that we could end up with days or maybe even weeks of being aware that something is going on that we need to investigate and fix. If we think about maybe a filter or a filter cartridge getting blocked up, if we can detect that early enough, it might be that we can schedule some maintenance on that in a few days' time and deal with it as a run-of-the-mill maintenance activity as opposed to an out-of-band emergency response because the filter's clogged and we've got the process tripped completely. Again, if we then have a paired signal feeding into the dynamic operating envelope, we're giving ourselves even more time. And using a combination of clever analytics and the data that we've got, we can increase the amount of time we've got to respond to potential incidents and detect them earlier. If we take that and apply that to the overall system that we're looking at, so if we go back to our compressor, then if we've got a list of all of these different signals that we know we've got coming in, then we can see at which point each one of these is at. So we can see on the right-hand side, we've got a couple of issues here where we've actually hit the trip limits on some of the signals. On the left-hand side, we can see there's some that are in our dynamic envelope that we've detected there's something going on, and we're on our way to a high or a low level trip, but we're not there yet. And that's the best opportunity that we've got to be able to step in and do something about it early. So how does all of that tie into equipment health and efficiency? If I go back to my original display that I showed you, we've talked about the section in the middle here where we're talking about individual signals. So that might be individual temperatures or speeds or vibration sensors or whatever that we can then apply our normalized or dynamic operating envelope to, so that we can detect abnormality early and then feed that back into this screen. Now, that's great at a very low level. That's giving us really detailed information on individual instruments hooked up to a system. The next step with that information would be to roll that up into a subsystem. So on the left-hand side here, we can see these signals being pulled into subsystems to allow us to get a better feel for the context of the individual signals we're monitoring. So on this example, we can see that it's most of our subsystems are in a good state, but we've got a couple of issues that we need to look at with the inlet flow and the power to the unit. That might be something that's been detected that says, well, actually, there's a filter blocked upstream, which is restricting the inlet flow, or it might be a restriction on the amount of power that's available or something like that. Once we've got that in the subsystem level, then we can also roll it into an overall health score. Now, this is the really interesting bit about this, because if you take all of that information that you've already gained and roll it up, we can give this piece of equipment a score. If we can give it a numerical score, that's even better. In an aging piece of plant, it may be very easy for you to look at an overall control room display and look and find an alarm on every other piece of equipment that's there. So you might have 50 pieces of equipment, and 25 pieces of equipment have got some sort of alarm on them that needs some sort of attention. But at that level, it might be very difficult to understand whether that is a little weep in a pump, which needs to be dealt with, but is not nearly as critical as a significant vibration in a compressor, which might bring down a multi-million piece of equipment, multi-million-pound piece of equipment. We need to be able to kind of give some context round about that by providing more information with the data. So if we can score a piece of equipment and give it a health score, then that gives us the ability to prioritize what's going on. So this piece of equipment you can see is maybe 95% healthy at the moment. It's got a couple of issues, but nothing very significant. If we take that sort of information and tie it all together, then we can build displays like this. And this, again, helps our engineering community, because if we roll this up, it allows them to immediately see, right, okay, big issue with equipment 5, that maybe needs my top priority and my top attention today, whereas equipment 1, we know there's a little issue there, but it's not my top priority. Now, because that's all been driven by analytics, we've then got the ability to be able to feed other contextual information in there. So maybe if we go back to this display here, maybe on the left-hand side in our subsystems, maybe the suction filter has a higher priority than pressure. And we might double weight that and say, okay, if we've got a suction filter fault, that's actually worth losing 10% of my health over, or something like that, and putting some weighted analytics in place to allow things to be prioritized effectively. The other thing we can do is use sparing information. So if we were applying this to a situation, let's say we've got 3 main oil line pumps, but we know that we only need two to be operational at any point to be able to get full capacity out of our system, then we can put that sparing information into the calculations as well, so that we can build an overall picture of, okay, my main oil line pump system is in good health just now because I've got two pieces of equipment which are healthy and they're running, and I've got a third piece of equipment which is healthy and is in standby, ready to go. Again, this is not just about calculating analytics to help us with the efficiency. It's about presenting the information in a really good way to allow engineers to make really fast decisions, rather than have to mentally compute on what the information is that's being presented to them. They can immediately see, okay, here's where my priority should be. How does this help in practice? Well, let me tell you about a few wins that we've had with this type of situation. So one of our customers has a paired signal detection, which identified a deviation on a pressure controller. That eventually would have caused a process trip. And by detecting that early, the team were able to avoid a deferment of 20 million barrels of oil equivalent. At that time, $1.2 million. Another customer had a experience where they realized their return on investment in 9 months. Through several different examples of several different things they caught, but one of the most significant ones being a 20-day unplanned shutdown that was avoided due to the improved monitoring. Estimated average of 500,000 a day, £10 million saving there by avoiding that 20-day unplanned shutdown. And another paired signal here where we identified a deviation on a scrubber process. And that deviation, had it been allowed to continue, had the potential to cause 45.6 million barrels of deferment, or 3.1 million. So just to summarize what I've covered there and what I've said there, real-time data used in conjunction with other data sources provides us a fantastic opportunity to convert that data into information that can be used. And we do that by using analytics. The appropriate information can then be directly increase the efficiency and the reliability of equipment and assets. But it really is key that we have effective user interfaces and user experience that allows us to use the subject matter experts that we have within our organizations to their best ability, have them focus on the right things so that the business gets the benefit out of that. So I seem to have rushed through that quite quickly, and I know you're going to get an opportunity to ask questions in a few minutes, but I'll just leave my contact details there. If you want to reach out to me, then you can feel free to do that. And I'm going to let Christopher just jump back in and take the next bit, please.